So I realize it's maybe dangerously late in the meeting to introduce something completely new and different, but I'm going to talk about the sun. I'm going to talk about some plasma astrophysics. There are lots of complicated words in this title that hopefully I'll explain what they are as we go along. So two of the key outstanding problems in solar and by extension stellar physics are why is the atmosphere so hot and what accelerates the outflowing wind. So in the top right image, we are seeing observations of multi-million degree plasma in the sun's atmosphere. This is kind of confusing because the surface of the sun is only about 5,000 degrees Kelvin. You know, the assumption would be that most of the energy to heat all of the stuff the sun is made of is coming from the nuclear fusion in the core, and you would assume that as you walk away from that fire, things get gradually cooler. But what we find is that when we go from the surface to the outer atmosphere, the temperature jumps by a factor of 1,000. And this is then related to, kind of tightly related to the fact that this injection of energy that provides this heat also forces an outflow, and we see observations of that outflowing solar wind in the bottom image. So we have some nice new observations from two major missions which have flown for the first time kind of in towards the sun that are revealing some of these secrets. But eventually, the ultimate source of the energy to heat the plasma and drive the wind comes from the magnetic field. So it's magnetic forces that dominate the plasma evolution in the atmosphere there. So what do we know about the sun's magnetic field? Well, here we have on the left some observations of the line of sight component of the magnetic field on the solar surface. And we see lots and lots of little positive and negative polarities, north and south poles. And if we then look at the multi-million degree plasma in the atmosphere, you can see that it seems to be brightest over the top of these so-called active regions where the magnetic field is strong. And this is the first clue that the magnetic field is really controlling the dynamics there. But one of the major things that hampers us from understanding how this happens in detail is that we can't actually directly measure the magnetic field above the surface. So we can measure the magnetic field on the sun's surface, but essentially not above. So then in order to figure out, well, what does the magnetic field structure look like and how does it determine all of these dynamics, we have to make some kind of model, some extrapolation of the magnetic field in the atmosphere. And there are various different assumptions you can make about what that model looks like, and I don't have time to explain them now, but regardless of what you choose for your model, you end up with something that looks a bit like this hairy ball in the top image. All of the curves on that image are magnetic field lines, and they've been colored depending on whether they're closed, that is, they're anchored at both ends in the sun's surface, or whether they're open, whether they extend from the sun's surface out into the heliosphere. And if we compare the structure of these magnetic field models then to observations of the atmosphere, what we see is that the open field regions are very well correlated with dark patches in the overlying atmosphere. So this is because the plasma is essentially constrained to follow the magnetic field lines. Plasma can flow along magnetic field lines, but it can't flow across them. And so in the open field regions, the plasma is free to flow outwards to form the solar wind. Hence, those regions have lower density, and that's why they appear darker. So I was going to talk about flux cancellation, reconnection, and how that might be providing some of the energy. So I should define what these things mean. The first thing I'm going to tell you about is what is flux cancellation. We've now zoomed in. These are observations from a ground-based telescope. We've zoomed in to a small part of the sun's surface, and you can see on the right the optical emission, and we've got a sunspot in the center. And then around that, you see this bubbling. The bubbling is a signature of the fact that, as we heard yesterday, the outer layer of the solar interior is undergoing convection. So it's like looking down on the top of a pot of boiling soup or porridge or whatever you have on the stove. And then if we go and look at what the magnetic field is doing, then on the left, we have the magnetic field observations, and we can see these positive and negative magnetic polarities. You observe them on all scales, and they're highly dynamic. And the little magnetic fragments, if you like, are merging and splitting and appearing and all sorts of things. So flux cancellation, what we mean by flux cancellation is just when you have two magnetic polarities of opposite signs that come towards each other and then seem to disappear or cancel. And until recently, this was not really considered greatly in terms of understanding these heating type problems that I talked about, because it wasn't really observed to occur all that frequently. But new high resolution observations are revealing much more mixed polarity flux on the sun's surface. And the latest analysis suggests about that this flux cancellation rate is like an order of magnitude higher than was previously thought. And so this motivates us to re-examine what the implications are for flux cancellation on the surface in terms of the evolution in the overlying atmosphere. And what I will try to convince you of is that one of the implications of flux cancellation on the surface is that we'll induce a process called magnetic reconnection in the sun's atmosphere. So what is magnetic reconnection? A cartoon picture is that it's just some sort of breaking and rejoining, reconfiguration of the field lines, the magnetic field lines in the plasma. And the point is that in most astrophysical plasmas, this is prohibited almost everywhere because of the extremely high magnetic Reynolds numbers. And when you're in one of these high Reynolds number plasmas where reconnection is prohibited, you can store a lot of energy in a magnetic field by stressing it. You can essentially think about magnetic field lines as behaving like rubber bands. You can store energy in the magnetic field by stretching those rubber bands or by twisting them around one another. And then the only way to liberate that energy is to snip the rubber band and allow that release of stress and conversion into kinetic energy and heating. So that's what reconnection does for us. And it can happen in very small regions of your plasma domain where intense electric currents develop. And this is what's happening on the sun all the time. Remember the hairy ball picture and the fact that the surface is churning. That constantly churning surface is constantly energizing the magnetic field. It's pumping energy up into the magnetic field. And if we can then liberate that as kinetic energy and heat, then we can start to explain things like the high temperatures and the outflowing wind. Now, as a brief aside, people aren't just thinking about reconnection for the sun. It's proposed to be relevant for explaining phenomena in all sorts of other astrophysical plasmas. Here's a couple of studies on reconnection for flares around black holes. I think it's my laptop. Don't know what's going on. As well as it being proposed as a source of bursts of relativistic particles and or disruption of jets in objects like AGN. Right, but I'm going to stick to the sun. Our idea then, our proposal is that you've got this constantly churning surface of the sun. There are flux cancellation events happening on all sorts of scales, and associated with each one of those is some sort of reconnection process marked by the red stars in my nice sketch here. And each of those reconnection processes will be depositing heat into the plasma and inducing an outflow. So in order to test this idea, we've performed three-dimensional MHD simulations. We take a kind of simplified configuration that is somehow representative of a region on the sun's surface where we have opposite polarity, and we solve for the plasma variables in the magnetic field in the overlying domain. We take a system with a few different polarities, and then we essentially impose a boundary flow that pushes two opposite polarities together to cancel in the same way as what we observe on the sun. And without going heavily into the details, essentially what happens is that in the overlying atmosphere, we do indeed form an intense small layer of strong electric current within which this reconnection process occurs. And the reconnection process launches a hot a jet of heated plasma up into the domain, and around about 3/5 of that magnetic energy that comes into our electric current sheet is converted into kinetic energy by work done on the plasma, while the rest just locally heats the plasma via ohmic heating. Now, one drawback of essentially all MHD simulations when applying to the sun's atmosphere is that we can't access the plasma parameters due to computational restrictions. We can't run with a realistic magnetic Reynolds number. And so then in order to get some kind of quantitative idea of what this implies for heating, we need to resort to some sort of mathematical models which will allow us to scale up to parameters that are appropriate for the corona. So using geometrical arguments and what we know about magnetic reconnection theory, this is what we did. And we come out with numbers which I don't imagine will mean anything to anybody in the audience, but essentially the overall energy release that you might get from a whole bunch of these different events is of a similar order of magnitude to the losses that we see, the radiated losses from the corona and the chromosphere of the sun as well. So in principle, there seems to be enough energy being liberated by all of these processes to explain at least some contribution to the heating process. Right, so I'll just finish with a summary. Magnetic reconnection is a fundamental process in astrophysical plasmas. It facilitates explosive conversion of magnetic energy into other forms. There are many open questions like the relationship with turbulence, how the macro and micro scales couple, how the energy is partitioned, and so on. I'm mostly interested in reconnection for the sun, but if you think magnetic field dynamics and magnetic reconnection might be important in your favorite astrophysical object, and I'm very happy to discuss it. If you're interested in learning more about reconnection, particularly if you need a cure for insomnia, I can recommend this excellent review article, which runs to 150 pages, and which will tell you everything you could possibly want to know. And finally, I guess reconnection is responsible for plasma heating, jet acceleration, and wind release in the sun and beyond. Thank you.
So reconnection, the location of reconnection in the sun, we know about where is it because we know where is the corona. But if we were to extrapolate to, say, these guys with accretion disks and AGNs, how high can the physics of the sun explain any reconnection? May explain any reconnection of any use for an accretion disk?
Yeah, I mean, I guess there are some parts that are somewhat and I mean, anywhere where you have some kind of corona above like a higher density turbulent thing, then you'll presumably have something like we have for coronal heating. I mean, the what I've drawn here, this is just a sketched idea, and the idea from the sketch is that here you have oppositely directed field lines, so it's a good configuration for reconnection, and they claim that this can induce relativistic particles. One thing, it's not coming back this time. One thing that I guess is certainly the case is that reconnection kind of is fundamentally different in 3 dimensions. You really have to model it in 3 dimensions. And so, yeah, I would always take a bit of a pinch of salt for sort of 2D sketches. But yeah, to understand where it happens, you need to understand the magnetic forces and essentially where you're going to form those electric current sheets. And so you need to do a big 3D MHD simulation or some clever theory, I suppose.
Any other questions for David? And I'll ask about something. So this, you explained open and closed lines, right?
Mm-hmm.
What fraction of lines are open and closed, and is it statistically changing with some time scale?
Good question.
Depends on height.
Sure, yeah, it depends on height. At the surface, I don't know, there's like, I'm gonna say maybe 25-30%. It probably depends on the solar cycle. Yeah, depends through which the surface field goes through a I mean, let's see, the overall amount of open flux essentially is not going to change very much, but then the closed flux should be higher in solar maximum where you've got some more of the sunspot regions, but I don't have the numbers to hand, sorry.
Okay. Let's thank David again.
Okay, thank you.